All right. Moving along, we have our feasibility study of high-powered human exoskeleton capable of high-altitude flight with Mike.
How's everybody doing tonight? All right. So, I actually have a confession to make. I am not an ECE major. I am what you would call a robotic engineering major. So I'm 1/3 ECE, but being Italian as well, I'm more Italian than ECE. So I'm also a grad student here, so as many of the other grad students and some of the professors can tell you, we like using really big fancy words to make all the time that we spend not with our families and loved ones and don't sleep, just so we can make ourselves feel a little bit more important at the end of the day. So today I'm going to be going over a feasibility study of a high-altitude powered, oh wow, I messed that up, feasibility study of a high-powered human exoskeleton capable of high-altitude flight. So in other words, Iron Man, how super is the suit? So first, I have to go over, because not everybody in here has the intellectual hierarchy of an RBE major. I have to go over this. So a robot is usually comprised of 3 main parts. It has a mechanical part, so like the physical structure of the device, an electrical component, so the stuff that we just put in a box and yell at when it doesn't work, and some kind of computer, to, ones and zeros and tubes, series of tubes. So everybody knows Iron Man, right? So you've probably all seen the movie, but let's kind of go through this. Let's see. Oh wow, this is actually working. Now, this is why we like to demonstrate that it's very important that you do calculations out beforehand, no matter if you're a freshman or someone like Tony Stark. So we're gonna take a little bit of a look into that, of why that just happened. So as I tell all my 1001 students, try not to think in the real world, because no one actually really understands that. So pretend you're in Narnia. Now the first thing you need to do when you're doing a force analysis is your coordinate system. That way you can just draw an arrow on the page and really hope that your professor gives you 1 point for really trying. So if we look at the Iron Man suit profile from the side, we have the big orange dot in there is the center of gravity. So that is the weight of Tony Stark with the boots. Then we have a thrust force acting up from the bottom. So if the thrust is much greater than the weight, using our equations of equilibrium, that is not going to equal 0. So you're going to have an ouch moment, propelling Tony back into the wall. So probably after he realized this, he probably went back, used some free body diagrams, equations of equilibrium, and why not MATLAB.
Day 11, test 37, configuration 2.0. For lack of a better option, dummy is still on fire safety. If you douse me again and I'm not on fire, I'm donating you to City College. All right, nice and easy. Seriously, just going to start off with 1% thrust capacity. In 3, 2, 1. Please don't follow me around with it either, because I feel like I'm going to catch on fire spontaneously. Just stand down. If something happens, then come in. And again, let's bring it up to 2.5.
So
3,
again,
2,
the importance
1.
of doing calculations out beforehand, and getting someone like me, a grad student, to actually do the grunt work for you. Although, as many of you are about to see, being a grad student and eventually going over multi-million-dollar cars would probably get you kicked out real quick. Although once you actually, pay attention to Newton's laws, where for every action there's an equal and opposite reaction, and you kind of balance yourself out, you'll start to look like a ballerina in the air. Something like that. So again, we have, if we're going to look at this from a simple perspective, we have our coordinate frame. Again, the center of mass, thrust from both the boots and the repulsor arms, giving us a horizontal yaw force, or a yaw moment. So this might be good in the Disney blockbuster movies, but there are actually some practical applications to building suits like this. So many of you have seen all like the GoPro footage with all the Red Bull wingless flight or winged flight suits that they go zipping through mountains and whatnot. But it's not really powered. You have to go up in a helicopter and sign a giant waiver before you go off and do that. Or you can be like this guy whose name I completely forgot how to pronounce, and be a crazy Frenchman and fly across the River Thames in this giant winged suit. The problem with this is both of those things are upwards of $50,000, and unless you feel like not going to WPI for 1 year just for crashing into the ground, you're probably not going to go off and do that. So another thing that you have to consider as being awesome as Tony Stark is there's a lot of components. Now, I have trouble enough tying my shoes in the morning, so having a robot actually put together something as awesome as the Iron Man suit would be very beneficial to me. The only problem is, and as many of you who know me can probably tell, I make pretty simple math errors, and to be going on and having the robot put it on these very expensive, very unforgiving plates on certain parts of my body, I want to make sure that there's some kind of tolerance put in place, because if one thing doesn't line up right, yeah, that's not going to be a good day. But thankfully, there are people who are much more better at speaking and actually doing something like this. So the ABB robotics is a lot what they use to build and paint cars. And this was actually an older video from a couple years ago, that they have enough precision to weave the robot tip in and out of the cans. Now, this is a pretty kind of robust control. I might trust them putting on, maybe an arm plate or two, but anything below the belts, we're gonna leave it up to manual control on that one. So, go into some of the electrical components. The main power source for Iron Man's suit is the chest arc reactor that he made in a cave from missiles. It's able to dim fluorescent lighting. Ominous fashion. Now, like I said before, my math isn't always as great, and I actually realized how wrong I was during the break, so this slide is completely inaccurate, but you're going to laugh at my joke anyway. So, assuming that it actually said 3 gigawatts in that, that's about, the Hoover Dam is about 2 gigawatts, and that's 1.5 times larger than the Ordo solar project, so that's the big solar project out in the middle of the desert, and 2 times more powerful than needed to run the DeLorean. So that's a lot. So going into the computing side of it, as you may see that, having a giant exoskeleton suit is pretty cool. You can punch through walls, but if you want to do some other cool things with it, like, target bad guys rather than the civilians, being able to recognize different people and know, that's James Rhodes, even though he's a different actor in every movie, or, go through and stabilize flight and realize that, oh wow, a tank shell is about to come in and hit me about 2 seconds before it actually does, you're going to want some pretty heavy computing. Now, all of these things exist. Many of us here, and I'm pretty sure we're going to have a Connect demo coming up, you're going to see some facial recognition or some body tracking. So that does exist. Advanced targeting systems, a lot of people here might go off and be able to target a fly on some kind of bad guy's vest from space or something, because that's what bad guys in James Bond do, and that's what a lot of us strive to be sometimes. And then we have everything from flight stabilization to quad rotorcopters to B-2 bombers. The only problem with this is there's going to be a lot of computing involved in this, and the way it's handled in Iron Man is through Jarvis or Jude Law. So some of the actual computing AIs that a lot of people have heard of is Watson. So he was on Jeopardy a little while back and kind of beat the pants off of everybody. And we also have Siri. But there's a large jump between Watson and Siri. Watson can go on and get words right. And because people ask Siri, where did I put my car keys, and expect a valid response, we're probably not anywhere close to having someone like Jude Law tell us that, a tank missile is coming at us or something like that. So there actually are some pretty cool exoskeletons out there today. This is the HAL suit. I wonder why they called it that. It's being developed at the University of Tokyo, and its main purpose is elderly assistance. So for people that aren't really able to, get out of bed and do daily tasks, they would, roll over and I guess put this on. And I don't know, maybe, who knows. And they have surface electrode sensors, so sensors that could just, through skin contact, can measure the electrical signals that are being sent out through the muscles to help assist in daily tasks. Then we also have the XOS. It goes by a bunch of different names. You've probably seen it as the Raytheon Hulk, and the University of California, one of them, leg suit that helps people walk. So this provides active assistance, and it's designed from helping people walk to helping soldiers carry heavy loads on the battlefield. The only problem with this, as you might tell, is that it needs a tether, so you're probably not going very far on the battlefield. Or you run up to the bad guy and you're just about to punch him and you pull out the cord. That's kind of embarrassing. Made in America. So what to take away from my attempt at a lecture is that I'm sorry, but robotics is the future. Sometimes comics do get things right, other times not so much, and what you learn here can actually be applied to build awesome kind of things, and the only limitation is your imagination. So, thank you guys.